In this video, we're going to be talking about what we do when we want to add integers together in embedded systems where all of my integers are represented using binary numbers or bits. And in order to do that, what we're going to do is we're going to have to sort of unpack a binary adder. And we're going to start by looking at unsigned integers, which I can shorten and often will to uint. So we'll start with a half adder. And what a half adder does is it takes exactly 2 bits and it will add them together. And the output is going to be both their sum and an output carry bit. And so you'll see that the logic gates are composed of an AND gate and an exclusive OR. And we'll just look at how the logic of this works. So we're going to get an input. Let's look at all possible values of A and B, 0, 1, 0, 1. B is going to be 0, 0, 1, 1. Sure. So the output for the carry, which is the exclusive OR, it's only going to be 1 when A is true and B is not true, or when B is true and A is not true. So it should be 0, 1, 1, 0. False, 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 false. So false. So let's look at the output of that. So let's look at the sum itself. The sum is the exclusive OR of A and B. So it's equal to 1 only when A is true and B is not true, or when B is true and A is not true, but not when they're both true. The carry is just the AND of A and B. So what's happening there is we are exceeding the possible values that we could get out of this. So if I add 0 and 0, I get 0. If I add 0 and 1, I get 1. If I add 1 and 1, I get 2. Well, with a single bit, there's no way to represent a value of 2, and so I would essentially need to carry to the next bit place. So when that happens, I get that AND, so that it's going to raise a carry flag in my embedded system. We'll talk more about the detail of that later, but essentially what we're doing is we're adding things together, but when we get an overflow, and if you've checked out my video about numbering systems, that might make more sense, but when you get an overflow, we need to carry on. The same thing happens when I have decimal numbers. So if I have 90 plus 15, then, right, I'll even write that down, 90 plus 15 with decimal numbers. I've got 5 is 5 plus 0. Then I've got 9 plus 1. Well, that's 0, carry the 1, I get 105. That's the same type of idea, except we're doing it with binary numbers. The problem with this is that if I need to repeatedly add or subtract or do other things like that, I'm not carrying anything in. And so that's where I might use what's called a full adder. A little more complicated in terms of digital logic here. I need 2 exclusive ORs, 2 AND gates, and a OR gate to make this happen. And essentially I've got an input carry, and then I also have an output carry. And then I have the sum. So the sum, essentially we're doing the same thing, except we might be carrying information in. So let's look at what happens is we get the carry out, and it serves as like a flag, again, a signal to our embedded system that I've overflowed the amount of numbers that I'm able to use. So the logic table for this, let's build, it's a little more complicated. Let's say I've got A and B and C in. So those are 3 different inputs. So let's go through all the possible cases. 1, 1, 1, 1. This is 0, 0, 1, 1, 0, 0, 1, 1, and then 0, 1, and so on. So this is our inputs. Then on the outputs, I'm going to get C out, or just C, the carry bit, and then I'm going to get S, which is the sum. So it turns out that executing the logic circuit that I showed you to start, we're going to end up with the following. We're going to get 0, 0, 0, and then we're going to have a 1, and then we're going to have 0, 1, 1, 1. And the reason for that is that if I either add two ones together, I exceed what a single bit can hold, or if I add more than two ones together, I can exceed what a single bit can hold. And then the S, the sum, it's equal to 0 when everything is 0. It's equal to 1 anytime there's a single 1. And then it's going to be equal to 0 if I exceed, well, if I get two ones, right? Because it's overflowing. It looks like it's a different number than it is. And so if I finish this out, I've got 1, 0, 0, 1. And you can think about that for yourself, whether or not all of that logic totally makes sense. But if you think about it, I'm getting a sum of 1 if I take 1 plus 1 plus 1, because that's equal to 3, which is bigger than I can handle with a single bit, which can only go up to a value of 1. But if I go right, if I draw a circle, and let's say this is 0 and this is 1, well, I can go up to 1. That's adding 1. Then I go again, and then it looks like a 0. Then I go one more time, and it looks like a 1. So that's how that works. It turns out that the output of this full adder, isn't an adder a snake? Anyway, little snaky there. Pew, pew, pew. Pew, pew. The output of the full adder is a 2-digit number where C out is the most significant bit and the sum is the least significant bit. So in other words, I get 2 bits. This one is C out and this one is S. So I put in 3 things. The actual sum that we can hold, at least in terms of doing this for a single bit number, is represented there. And obviously we could extend this further if we were going to add more and more bits. Right, so how does an overflow happen? Well, when adding 2 unsigned numbers in an n-bit system, a carry flag occurs if the result, if I could spell, if the result is larger than the maximum unsigned integer that can be represented. In that case, it would be 2n minus 1. When we subtract, so that was adding, when subtracting, we do what we call borrow. So I'll put little quotes around carry. So we borrow when we get a result that would be negative, or we go below 0. So when result should be negative. And that's just working the opposite way around that overflow circle I showed you before. It turns out that in an ARM processor, that the carry and borrow flag is the same, and it's a 32-bit processor. It turns out that bit 29, so that's the, again, we count from 0, so that's like the 30th bit. That's the carry and borrow flag. And essentially the logic for that is if carry is 1, we're going to have a carry for unsigned add. And if carry is 0, then it's not a carry. And if we're doing unsigned subtract, we don't borrow when the carry is 1. No borrow. And we borrow when the carry is 0. So essentially, the carry is equal to not borrow. Now, if I want to work with signed integers, there's a couple of different ways to do it. I'm going to talk about 2 in this video. So the first one I'm going to talk about is 1's complement. And I've seen this represented where it's like alpha with a tilde above it. I think I'm just going to use OC to represent it. So when I do this, the values I can represent go from -2 to the n minus 1 overall plus 1 to 2 to the n minus 1 minus 1. So in this system, there are 2 to the n minus 1 unique numbers. In other words, if I had like n equal to 2, I would have 3 unique numbers. Okay, and if I take the original value, I'll call it alpha, and I add it to alpha tilde, it's equal to 2 to the n minus 1. We'll check that here in a moment. So how does this work? Well, the 1's complement of a negative binary number is the bitwise not of its positive counterpart. And one thing I'm going to add is, let's say I've got a n bit, let's say n is equal to 4. So that's 2 to the 4. The possible values, if we were working with an unsigned integer, would be equal to 16 values. What we do is we take that range from 0 to 15 and we shift it so that way I'm going from a negative number, which is -7, to +7, where 0 is sort of the middle point of that. Okay, so that's, again, it's 2 to the n minus 1 unique number. So now instead of having 16, which would go from -8 up to 7, I would have only 15 possible values going from -7 up to 7. Okay, so the way that we would do this is we take a positive value, and let's say, right, for example, I've got +7 base 10. Okay, in binary, well, let's use 5 bits just for grins and giggles. In binary, that's 0, 1, 1, 1, 1, base 2. To get the -7 in base 10, I'm going to simply take everywhere that there's a 0 and make it a 1, and everywhere there's a 1 and make it a 0. That's just a 1's complement. And if I were to add these things together, right, so +7 base 10 and -7 base 10, I would expect that to be 0. Let's see if that works. Well, if I take 0, 0, 1, 1, 1, and I add 1, 1, 0, 0, 0, I just do a bitwise add. It turns out there's no carries here. So this is 1, 1, 1, 1, 1. Huh. That's equal to 31 base 10. Well, if 2 to the 5th is equal to 32, that's the same as an overflow back to 0. So this is one of the challenges with 1's complement, is that instead of having a 0 equal to 0, having all 1's is also equivalent to 0. So that actually motivates us looking at another approach. And that approach is what I call 2's complement. I don't call it that. That's just what it's called. And again, I've seen this represented using an alpha with a bar over it. I don't really care what you use. I'm going to primarily just use TC. So this has a range from negative 2 to the n minus 1 up to 2 to the n minus 1 minus 1, which has 2 to the n unique numbers, and a plus a bar is equal to 2 to the n. One of the reasons that this works better is that I don't have like duplicate zeros. If I exceed my limit, I'm going to hit 0, and I'm going to discard any overflow. So here's how this works. To get the 2's complement is you take the bitwise naught of the positive value and add 1. Let's see that in practice using an example. So if I take the 2's complement of 3, well, that's the 2's complement of, again, let's use 5 bits for grins and giggles. 3 is represented by 0, 0, 0, 1, 1. So if I were to take that's equal to negative 3, right? I want to represent negative 3. Negative 3, if 3 is equal to 0, 0, 1, or 0, 0, 0, 1, 1, negative 3, first of all, I take 1, 1, 1, 0, 0. So I'm taking everywhere there's a 0, replacing it with a 1. Everywhere there's a 1, replacing it with a 0. And I'm going to add 1 to that. So that'd be 0, 0, 0, 1. And when I add that together, I get 1, 1, 1, 0, 1. Now, let's check 3 plus negative 3. How does that work? Well, I've got 1, 1, 1, 0, 1. That's the negative value, plus 0, 0, 0, 1, 1. If I add those together, maybe I should rewrite this a little bit. So I've got 1, 1, 1, 0, 1, and this is 0, 0, 0, 1, 1. Add those together, right? So 1 and 1 here is a 1 with a carry. That's a 0 with a carry. That's a 0 with a carry. That's a 0 with a carry. That's a 0, and then we put the overflow here. And it turns out that what I'm going to do is discard that overflow. Discard 3 cards from your hand. So we're going to get rid of that overflow, and so I'm left with a value of 0, which is what I am hoping will happen in this case. Overflow is different from carry. It's the flag V, which is bit 28 in our embedded system for an ARM system. That's the overflow flag. That's hard to say. Overflow flag. Overflow flag. Okay, so the last thing to talk about here is how I know whether or not data is signed or unsigned. Signed versus unsigned, right? So if I have A, which is 1, 0, 0, 0, 0, and B, which is 1, 0, 0, 0, and I want to calculate A plus B, it really matters whether or not the data are signed or unsigned. The CPU doesn't know, right? Programs and computers are only as smart as their programmers. The compiler or the programmer itself needs to interpret the carry or overflow flags. Again, hard to say. So it's really up to the compiler or the programmer to interpret the flags. That would be the C and the V flags. If it's unsigned addition, we want to check the carry. If it's signed addition, we check overflow. When we're using a high-level language like C, the compiler knows based on how this is declared in your code. So in a high-level language, we declare that something is an int, which means signed, or a uint, which is unsigned. And that helps the compiler interpret what's going on. Another thing to tack on here is just that in 2's complement, the same hardware works for both signed and unsigned addition and subtraction. Signed also works for hardware, also works for multiplication with unsigned data, but that's not true for division. So the big thing to highlight, and the reason we care about 2's complement, is it simplifies hardware because we can use that hardware for addition, subtraction, whether the numbers are signed or unsigned, as well as multiplication. So the only thing that I would need special between signed and unsigned is if I'm doing division. That's all for this video. Thanks for watching.